Okay, today I'll be presenting the paper Breaking Through Binaries, Compiler Quality Instrumentation for Better Binary-Only Fuzzing, published at the USENIX Security Symposium in 2021. The authors are Stefan Nagy from Virginia Tech, along with researchers from UVA and Virginia Tech. This paper addresses an important challenge in software security: how to make fuzzing work well when we only have access to binaries instead of source code. Fuzzing is one of the most effective automated techniques for finding vulnerabilities in software, but many fuzzing techniques rely heavily on compiler instrumentation, so they can only work when we have the program source code. Um, this is not ideal though, because many real-world targets are closed source binaries, and this includes proprietary applications, legacy software, commercial programs. For any of these, we can't recompile the program, so we have to rely on binary instrumentation. And this historically is a problem because it performs much worse than compiler-based approaches. This paper introduces ZAFL, which is a system that aims to bring compiler-quality instrumentation capabilities to binary-only fuzzing, while still maintaining comparable performance. So the main goal is just to get the trade-off of performance to not be as great. So fuzzing in general works by automatically generating large numbers of inputs to a program and then observing how the program behaves. This goal is to discover unexpected behavior such as crashes, memory corruption, or security vulnerabilities. Modern fuzzers often use a technique called coverage-guided fuzzing, where instrumentation inside the program reports which part of the program are executed, and that allows it to guide its future inputs and exploration towards new program paths. Um, but coverage guiding fuzzing relies heavily on instrumentation, which inserts additional instructions into the program to record execution behavior. If we have access to the source code, we can instrument the program during compilation using tools like LLVM. This allows us to insert instrumentation efficiently and with full knowledge of the program structure. But if we only have a binary, it's a lot harder to do that. So the two main approaches to fuzzing depend on whether the source code is available. Compiler-based fuzzing, we recompile the program with instrumentation added by the compiler. This is extremely efficient because the compiler understands the program's control flow and it can insert instrumentation like pretty much anywhere you want. It's very precise. The second approach is binary-only fuzzing, where the program is already compiled and we don't have the source code. Instead, we must modify the compiled binary directly. Binary instrumentation can be done using dynamic translators um, or static rewriting tools. A dynamic translator example is QEMU, and a static rewriting tool could be like Dynamist. Unfortunately, these tools are very limited. They usually have significantly higher overhead. They lack deep semantic information about the program, and they have difficulty implementing advanced compiler-based transformations that improve the effectiveness of the fuzzing. Because of these limitations, binary-only fuzzing typically finds fewer bugs and runs a lot slower than compiler-based fuzzing. So the key problem this paper is addressing is the gap between compiler instrumentation and binary instrumentation. Compiler-based instrumentation has the advantage of performing sophisticated program analyses. You can analyze control flow, data flow, register liveness, and it can perform advanced program transformations to help the fuzzers explore code more efficiently. Compilers can transform complex comparisons into simpler operations that are easier for fuzzers to solve, but like binary instrumentation tools often lack these capabilities. They operate on already compiled machine code, so a lot of the high-level program structures are lost. And so the main goal is to ask whether it's possible to design a binary instrumentation framework that has the same performance of a compiler instrumentation. And the system they introduced for that was ZAFL. ZAFL is essentially a compiler-style framework for binary instrumentation. Instead of modifying instructions directly inside the binary, the system first translates the binary into an intermediate representation, similar to how compilers work. This is important because when compilers instrument code, they have access to a rich internal representation of the program, and that representation makes it possible to perform the same sophisticated analysis that you need, like data flow, control flow, and dominance. Binary instrumentation tools usually don't have this advantage. They typically operate directly on machine code, so a lot of the program structure is gone. And DAFL addresses this problem by reconstructing enough program structure to enable the advanced analyses. The architecture has two main parts. As you can see, the first part is the static binary rewriting engine. The engine disassembles the binary and converts it into the intermediate representation that closely resembles machine-level instructions. The second part is the ZAX pipeline, which performs transformations and inserts instrumentation. So ZAFL consists of two main components. The first, wait. Okay, so ZAX operates on the intermediate representation and performs four major phases of analysis and transformation. The phases is listed: optimization, analysis, point selection, and application. This pipeline mirrors the structure of a modern compiler optimization pipeline, which is exactly why the authors describe the ZAFL as enabling like similar compiler quality instrumentation. Okay, so before we explore the ZAX phases, we have to understand why binary instrumentation is so difficult in the first place. When compilers operate on source code, they have access to all the structural information about the program pretty much. They know where functions start and end, they know types of variables, and they know the structure of the control flow. Once a program has been compiled into a binary, much of this information is lost. So binaries don't explicitly mark function boundaries. Instead, the program is just a sequence of machine instructions. Tools attempting to analyze the binary must infer these boundaries through heuristics. Another challenge is indirect control flow. Instructions like indirect jumps or function pointers make it very difficult to determine all possible execution paths statically. Additionally, register allocation has already been finalized by the compiler, and this means there are limited opportunities to insert new instructions without interfering with existing register usage. Finally, reconstructing the control flow graph is particularly difficult because binaries may contain optimizations such as inlining, tail call elimination, or jump tables, and all of these make the binary rewriting far more complex than source level instrumentation, and that's why early binary fuzzing systems struggled to match the compiler-based performance. So first phase, optimization phase, the goal of this phase is to transform the program to make it easier for fuzzers to explore deeper execution paths. Coverage-guided fuzzers rely on feedback signals that tell them whether their NP mutations are making progress towards new behaviors or not. The program contains large or complex constraints. Fuzzers will struggle to discover inputs that satisfy those constraints. For example, something that checks whether a 4-byte integer equals a specific value. It's very unlikely that it will get all four bytes right at the same time. So guessing that 32-bit value randomly is very, very low. So the optimization is fuzzing enhanced transformations, such as sub-instruction profiling, which breaks larger comparisons into smaller comparisons. So instead of comparison involving all 4 bytes, it's an individual comparison for each byte, so it can get incremental feedback. When the first byte's correct but the second is wrong, it will see partial progress, and then it will continue only on with the same correct first byte. So this allows the fuzzer to slowly evolve and find the input that satisfies the full condition. The authors emphasize that this phase must happen before the analysis phase because these transformations modify the control flow structure of the program. Once the program has been transformed, the later analysis phases can operate on the final control flow graph. Okay, so after the optimization phase, ZAFL performs a series of program analyses. This phase is critical because it reconstructs much of the semantic information that compilers normally have access to. The important analyses performed here are control flow graph construction, which represents the possible execution paths through a program. Each node corresponds to a basic block, and the edges represent possible transition between blocks. Having an accurate control flow graph is essential for deciding where instrumentation should be placed. The second analysis is dominance analysis. In dominance relationships, we say that block A dominates block B if every path to B must pass through A. This information helps identify redundant instrumentation points. So for example, if execution of block B always implies that block A has already executed, then instrumenting both blocks might be unnecessary. So data flow analysis determines how values propagate through the program and which instructions depend on which inputs. And register liveness analysis determines the value in a register that will be used later in the program. So this is important when inserting instrumentation instructions because we have to avoid overriding registers that contain values that are needed by the program. So these analyses can reconstruct enough information about the program structure to support safe and efficient instrumentation. So one of the most interesting technical ideas in this paper is the register liveness optimization. Register liveness analysis determines whether the value stored in a register will be needed later in the program. If a register is considered dead, so its value won't be used again, the register can safely be reused for instrumentation. This is important because when instrumentation code needs temporary storage, it normally has to save registers in memory and restore them afterwards. The save and restore operations are a large source of overhead, but if the system knows that a register is currently unused, it can simply reuse that register temporarily without saving or restoring anything. ZAFL uses the analysis phase to compute register liveness information for every point in the program, and this allows the instrumentation phase to insert code that is very safe and highly efficient and doesn't, you know, mess with any of the memory. Um, the later evaluation in the paper shows optimization had like a large role in reducing instrumentation overhead. The next stage is point selection, which decides where instrumentation should be inserted. Um, you might think that instrumenting every basic block would provide the most information to the fuzzer, but doing so would introduce a large amount of runtime overhead. Each instrumentation instruction consumes CPU cycles and slows down the execution of the target program. Since fuzzing involves executing the program millions to billions of times, as we've seen from our small reconstructed fuzzers from scratch, even a small amount of overhead increases can significantly reduce the throughput. So the goal of point selection is to identify the minimal set of instrumentation points that still provide enough coverage information. So you use the results from the previous analysis phase, and ZAFL removes instrumentation that could be redundant. For example, if a block has only a single successor, then reaching the successor implies that the predecessor must have been executed. In that case, instrumenting both blocks provides no additional information. By carefully pruning unnecessary instrumentation points, ZAFL reduces runtime overhead while still preserving useful coverage feedback for the fuzzer. Okay, now the final phase is the application phase. This is where instrumentation instructions are actually inserted into the program. This stage has to be handled very carefully to preserve the program's original behavior. One challenge is that inserting instrumentation may require temporary registers or additional instructions. If these registers are currently holding values that the program needs later, the instrumentation could corrupt the program state. So this is where the liveness analysis is very valuable, since by knowing which registers are currently unused, ZAFL can safely choose registers that won't interfere with the program's execution. The authors also note that condition code registers are particularly expensive to save and restore. So the registers that store flags used for conditional branches and restoring them incorrectly would change the program behavior. ZAFL prefers instrumentation locations where the condition codes are not live to avoid this issue. So yeah, these the carefulness of the application allows it to insert instrumentation efficiently without sacrificing correctness. Okay, so ZAFL implements 5 fuzzing enhancing transformations originally developed for compiler-based fuzzing. 3 of these improve performance: single successor instrumentation pruning, dominant base pruning, and edge instrumentation downgrading. The remaining 2 improve fuzzing feedback, so sub-instruction profiling and context-sensitive coverage tracking. These transformations help reduce instrumentation overhead and provide richer feedback to the fuzzer. The authors evaluated ZAFL using both synthetic benchmarks and real-world software. The synthetic benchmarks included the Lava M corpus, which contains programs with injected vulnerabilities. They also tested ZAFL on 8 real-world programs such as TCP dump, Readelf, Jasper, and BSD-tar. Each program was fuzzed for 24 hours using AFL with different instrumentation tools, and obviously multiple trials were run. So to kind of understand just how significant ZAFL's contributions are, it helps to look at why existing binary instrumentation tools struggle. So first, AFL QEMU performs dynamic binary translation during execution. So this is a very flexible approach, but it introduces a significant runtime overhead because every instruction has to be translated before execution. Another tool is AFL Dynast, which performs static rewriting. However, This lacks the sophisticated program analysis needed to support the advanced mutations and transformations. So most binary instrumentation frameworks were designed for debugging or profiling, not for fuzzing. And so as a result, they lack the infrastructure needed to perform compiler-style analyses like dominance analysis and register liveness analysis. So ZAFL addresses these limitations by designing a binary instrumentation system specifically optimized for fuzzing. So let's look at the evaluation results. The authors compared ZAFL against two widely used binary instrumentation approaches used with AFL. This was AFL QEMU and AFL Dynast. The experiments involved fuzzing multiple real-world programs and measuring the number of unique crashes discovered. Results show that ZAFL consistently discovers significantly more crashes than the competing systems. This indicates that the improved instrumentation not only runs faster, but also provides better feedback signals to the fuzzer. Better feedback allows the fuzzer to explore deeper and more complex execution paths. So it's an important result because it demonstrates the instrumentation quality directly impacts vulnerability discovery. So another metric that was evaluated was runtime overhead. Fuzzing effectiveness depends heavily on throughput. The more test cases the fuzzer can execute per second, the more program behaviors it can explore. Dynamic binary instrumentation tools like QEMU often introduce a lot of overhead because they translate instructions during execution. ZAFL avoids this cost by performing static rewriting ahead of time, and this means the instrumented binary can run almost as fast as a regularly compiled program. The results show that ZAFL achieves overhead around 27%, which is remarkably close to the overhead of a compiler-based instrumentation, and at the same time, it significantly outperforms AFL QEMU and AFL Dynast in execution throughput. This result is important because it demonstrates that a high-quality binary instrumentation does not necessarily require sacrificing performance. For many years, the fuzzing community has recognized the gap between compiler-based and binary-only fuzzing. Binary approaches always being slower and less precise and less capable of supporting advanced transformations. But this ZAFL pipeline shows that the gap can be significantly reduced. By reconstructing program structure through static rewriting and applying compiler-style analysis, they've demonstrated that binary instrumentation can achieve both high performance and sophisticated program transformations. This opens the door for more powerful fuzzing techniques to be applied to closed-source software. In practice, this means security researchers can more effectively analyze proprietary applications, firmware, legacy binaries, and anything that can't be recompiled. So while ZFL represents a major improvement for binary-only fuzzing, it definitely has its limitations. One challenge is handling heavily obfuscated binaries. Obfuscation techniques often deliberately obscure control flow, making it difficult to reconstruct an accurate CFG. Another limitation is self-modifying code, so the program modifies its own instructions during the execution. Static rewriting approaches can struggle to handle the cases correctly since the code is still being modified. Static rewriting isn't going to be the same every time. The current implementation also focuses primarily on specific architectures and binary formats, so extending the system to additional platforms would require a lot more engineering. Integrating ZAFL with hybrid fuzzing techniques that combine fuzzing with symbolic execution could potentially leverage the high-quality instrumentation to guide symbolic execution more effectively, but that hasn't really been explored that much yet. Yeah. So, in conclusion, this paper demonstrates just how close you can bring binary-only fuzzing to compiler-quality instrumentation. It reconstructs enough program structure through static rewriting and intermediate representations, and using this approach, it enables sophisticated transformation analysis that were previously only available in compiler-based fuzzing. There were significant improvements in crash discovery and fuzzing throughput, and overall ZAFL helps close the long-standing gap between compiler-based and binary-only fuzzing. Most binary instrumentation tools. Um, okay, so question one, why can't existing binary instrumentation tools do this already? Most binary instrumentation tools focus on general program analysis or dynamic translation, and so therefore they lack the deep compiler style program analysis and transformation infrastructure that you need for fuzzing specific optimization. As far as why not fuzz binaries with source code instead, many practical applications of fuzzing, you don't have access to the source code. You want to find vulnerabilities in proprietary software, commercial applications, firmware, legacy systems, and these are often only distributed as binaries, so you're not going to be able to have access to the source code. Does ZAFL work for obfuscated binaries? Not really, not reliably. Heavy obfuscation can disrupt control flow reconstruction, and that makes the static rewriting a lot harder. So we haven't figured out a way for ZAFL to work on obfuscated binaries that well. Splitting comparisons. Why do splitting comparisons help fuzzers? Uh, because fuzzers mutate inputs gradually, splitting large comparisons allows the fuzzer to get incremental feedback when part of a constraint is satisfied. That just allows it to incrementally develop rather than constantly guessing a massive possibility of combinations.